In this video, we will discuss a very important class of functions, which are the class of continuous function, right? So that's basically almost all the function in our discussion will be continuous. So let's start from the definition of being continuous. So being continuous just means like a function has a good limit, right? Which means your function change smoothly, right? So let me write down the definition here, right? Definition is a very natural extension of the definition of limit, right? So you have a function, right? Which is a function here. So y equal to f of x, right? So that's a function. A here is inside the domain of f, right? What's the meaning of that? Here is f of a here is well defined, right? We know what's the meaning of that. If you plug in a, you get a valid number, right? And so we say that the function, which is f here is continuous, right? Which means nothing bad happens at a number if what if as x goes to a here, f of x, right? So this should exist. So if that doesn't exist, the function is not continuous. And if this exists, this has to be equal to f of a. So that's our definition of being continuous. At the number a here, the limit exists, and also the limit equal to the function value, right? You don't have a jump, right? You don't have a gap or anything like that. So it's easy to write down what's the meaning of being not continuous, right? So not continuous means discontinuous, right? We say that f here is discontinuous at a, if what happens if there are three possibilities, right? And first one is f of a does not exist, which means does not exist, which means you have a hole there, right? Function value is undefined. And or the second one, the limit as x goes to a, f of x is doesn't exist, right? Might go to infinity or negative infinity, or it might be a greatly changing curve, right? And the third one here, all right, third one here, if they both exist, they are different, right? As x goes to a, f of x is different from f of a here, right? Let me try to sketch a picture here, right? A graph here to see three cases, right? The limit, the function is not continuous, right? At the given point. So we have our x-axis, we have our y-axis. We have three special points. One is -1, 1, and 2, right? So the first one is something like this, and goes down to here, circle, and go up. I can see that this is our function y equal to f of x. So at the first point, -1 here, So f of -1 doesn't exist, does not exist, right? So which means the function is not continuous at -1. And also the limit as x goes to 1, f of x, look at second point, it doesn't exist, dne, right? Because the left limit is 0, right limit is 1 if you have this is 1, right? This point here is 1. And also we know that as x goes to 2, by look at the picture, f of x is different from f of 2. They're different, right? So by our observations, f here is discontinuous at x equal to 1 to -1, right? So that as a 3-point, this function is not continuous, right? So by our discussion of limit, we know that whenever you have a polynomial or rational, right? So you can, when you try to evaluate limit, all you do is plug the number into the function. So which means this function is continuous at that point, right? So we get two very nice results. We call that theorem. And the first one here is because polynomials, if you want to evaluate limit, you plug in the number a here, so which means the function is continuous at that point, right? So this is true for every point. So our continuous function, a polynomial function, a polynomial function is continuous everywhere, right? No matter what is your value of a, this function is continuous at a, right? And second, remember if you have a rational function, right? So rational function, if you don't recall, the rational function is basically a ratio of two polynomials, right? So the domain of such a function is everything but numbers make the denominator equal to 0, right? So by our discussion before, right, using some very using the limit laws, right, and this function is also continuous when you try to evaluate the limit at a number which is not in the domain. All you want to do is plug that number into the function, so which means this function is also continuous at that number, right? At any point in its domain, right? So this is two easy results we can obtain from the limit laws, right? Now let's see an example, right? Let's see an example. Sometimes we want to make sure our function is continuous, right? So we have a function for what value of c, right, is f continuous on R, right? R here is a set of all real numbers from -infinity to +infinity. So we are given a function with a parameter which is c. So our function looks like this: f of x equal to cx squared plus 3x when x is less than 2, equal to x cubed minus cx when x is greater or equal to 2, right? So that's our function form, which contains a parameter, which is c, right? For different values, you have different functions. We are looking for a c value such that the corresponding function f is continuous everywhere, right? For some c value, this is not continuous, right? Solution, so let's see, let's try to find it, right? So continuous everywhere means continuous at all the numbers, right? Let's look at for what number this is for sure continuous. So less than 2, this is polynomial for sure continuous. So we know that, so the f here is clearly continuous, continuous on the interval from -infinity to 2 and from 2 to positive infinity, right? So that's because on both p's, this function is a polynomial, right? And so now the question here is whether our function is continuous at 2. And so our question here, let's see what is 2 first, right? What is f of 2? Function value at 2 is clearly plug that into the second piece because this definition here, this is h minus 2 times c. So we want to make sure the left limit, the limit is 2, right? But this function here is given by piecewise defined for sure. If you want to evaluate the limit, we want to evaluate left limit and right limit. So the left limit as x goes to 2 on the left side, we use this formula here. You get we get the limit is 4c plus 6. 4c plus 6, and the right limit as x goes to 2 on the right side, f of x is h minus 2c, right? We want to make sure the limit exists and also the limit equal to the function value. So this for sure agree with our function value. So we set up equation which is 4c plus 6 is h minus 2c, right? The left limit should equal to the function value, should also equal to the right limit, which make our limit exist. By solving this equation, you get 6c equal to 2. So c here is 1/3, right? So we can say that when c is 1/3, f is continuous everywhere. So this is basically we are starting from a function with a parameter, and we can identify this parameter such make our function to be continuous everywhere, right?